So, nonparametric correlations now. Pearson's assumes a linear relationship between the variables. And some non-linear designs. This isn't totally non-linear so much as it is linearities like, okay, whatever. One of them is Spearman's row. So what it does is it takes the data and ranks it. So it puts it all in order and gives each score a rank, like first, second, third, fourth, fifth. And then it correlates the ranks. So it doesn't force linearity, but it gets the data in a less curved pattern. It makes everything ranks. Spearman's row is not good if lots of data points have the same numbers. So if you're doing like a 1 through 5 type scale and decide that it's not linear, Spearman's row will not be a good option because lots of people have picked 5. So that means all the 5s are going to have the same rank. So it'll give you a warning / an error message that says like, don't trust P with lots of ties, I think is what it says. So the alternative to that is Kendall's tau. So Spearman's row is better for data with lots of different numbers. So lots of different scores without a lot of ties, so not a lot of the same score. Tau is better for data with lots of the same scores. So it's better for small samples and with lots of things have the same rank. And by rank, I mean that I take the scores, sort them numerically, and just give it 1, 2, 3, 4, 5. And then the correlation is on the ranks, not on the original data. And it gives you the same type of number, though. So the positive numbers mean the scores are going up together. The negative numbers mean there's one's going up, the other's going down. It just doesn't assume linearity. All right, so I'll run an example. These two will also work if you have non-continuous data. So let's say you have ranked data already. So we're going to pull up this data. It's called the World's Best Liar Competition. It's from the book. So we have where people placed in the competition for second, third. So that is not continuous data. That is ordinal data. It's ranked already. And a creativity questionnaire. So this is the liar data set. So what you can do is use the method function and you change it to Spearman or Kendall, depending on which one you're interested in. So I can calculate Spearman and Kendall with core function, but I don't get P. And since the point of this section is to calculate statistical significance for correlations, that's not very helpful. I can get Spearman with R core, but no Kendall, so not helpful. And then I can do everything with core.test, but you have to do them one at a time. So this is really why we're talking about core.test, other than the confidence intervals thing, because that's really awesome too. So what I want to do, let's look at the code, is I use the with function on this one to kind of show you both ways that you can do it. So I've got core.test, creativity, and position. So position is my ranked variable, so I wouldn't want to do Pearson on this because that is not continuous data. Okay. The creativity score, and I've got method equals Spearman, and then method equals Kendall. So I can run that twice, and we will get a warning. Okay. And so for Spearman, what it gives me is S. S is a measurement of covariance for ranked data. So mostly that gets ignored. But then the p-value. So true row is not equal to 0. Here's row. So the original score was 0.44. Oh, sorry, that's a totally different example. That's exam anxiety example. Never mind. I didn't say anything. So the correlation is 0.37. It's a medium negative correlation. As creativity goes up, rank goes down, which is kind of backwards, right? Until you think about that as a picture. So ranked data is hard to work with. So we've got position, first, second, third, fourth, fifth, and then creative. So as creativity goes up, position goes down. That would be positive. Wait. Position gets smaller. Okay, this way. I'm going to bust my face today. Just know. Here we go. She will not stay tight. So it's a negative correlation, so it's got to look like this. And we're saying as creativity increases, position decreases. But what does position mean in this example? It means I'm scoring first place. Right? So a negative correlation in this sense is kind of hard to interpret when you talk about ranks, because low ranks are usually a good thing. Right? It's the first, I got first place, and I have the highest score. It's still negative correlation. As I get more creative, my ranking score is lower, which is a good thing. So this is why you always draw a scatter plot. It means to make sure you understand what's actually going on, because if you say it's a negative relationship, as creativity goes up, you score worse, right? Which is kind of the way you think about it. Like as one goes up, the other goes down, but it's not the way I would interpret this type of data. Right? That being said, you get this warning message that it doesn't like to do Spearmans with ties. If you get that message, what it's saying is there are a lot of people who have the same, one of the variables is consistently the same. So I have lots of first, second, third place answers in here. So it doesn't want to do that. Then you should try Kendall's. So Kendall's is the next line down. It's the exact same code, just switch out the method piece. And it didn't give me an error this time. So Kendall's is calculated with z-score, so it's still significant, it's just slightly smaller. Kendall's will almost always be slightly smaller, because it tends to overestimate with a bunch of ties, but that's not always true. So it will be different, so 0.3. Still a medium correlation, same interpretation. So Kendall's is better with small samples and tied samples with lots of the same scores. And the way to tell the difference, if you can make a table on the data and it looks like a little small table, Kendall's is better. Does that make sense? Right. So if I did a table of the creativity score. Oop, not the whole data set. Try again. Okay, that has lots of different options, so not too many ties. But if I did a table of the position, that has lots of ties. That's what it means by ties. So that's when Kendall's is better. So Spearman's row, Kendall's tau are for nonlinear data, or data that has is not continuous, so ranks. So to use these, all your values still have to be numeric, even if it is actually categorical. To make it run, it has to be numeric, so it's a little bit of a like, ugh, with it. So if you have any variables that import with labels, you have to sort of defactor them. So as.numeric is the opposite to as.factor. Okay, so you can factor them and unfactor them, so we can make a numeric variable as well. So it has to be numeric even though it isn't. So another options we've done, Pearson, Kendall's, Spearman's, is what's called a point or a point biserial correlation. So point or point biserial. And that's correlating with a dichotomous variable, and I truly do have the right word there this time, dichotomous. You can only do correlations when they have two options for point biserial. If you have three options and they're not ranked, no go. So you can't do like, we had that example of none, football, and volleyball. I can't do a correlation with that. So correlations do assume some sort of either rank, first, second, third, fourth, or continuous variable. Okay. Or it's truly dichotomous. Okay. If you have three separate groups, ANOVA. Okay. So which is which? A point biserial is something that has a true dichotomy. It has no underlying continuum. And I really should change my example to not be gender, because there's lots of arguments over this right now, but we could talk about maybe sex. Genetically, there is a true dichotomy, right? One is X, one is Y. But things that have a true split, and there's no underlying continuum in that. A biserial correlation is something that you have forced into a dichotomy. So we force a pass-fail on classes but there really is a score underneath that. And so it is a point biserial, which would be RPB, which is a true dichotomy, or a biserial correlation, so RB, which is not truly a dichotomy. So think about it this way. If it's a point biserial, it has two distinct points, nothing in the middle. If it's just biserial, I have forced it to have those points, but it is not distinct. And if you can come up with a better point biserial example, that would be great. Now when you run these, it'll still say Pearson's product moment correlation, and it looks just like the other output. But what you have to do, so I did this with core.test, so I'm down here at point biserial, is I had to defactor it. So my liar data here, currently the novice column is a factored variable. So it says up here factor. If I do a little table, you'll see that. Okay. So it's the first time that they've ever been in a liar competition, or they've been in a liar competition before. Okay. And I just have to get rid of that factoring for a second. Okay. So I did as.numeric. So 76. Now you'll see it's a number 1 and 2. So I can switch it out. You could also make yourself a new column where it's the numeric version and the factored version to keep yourself straight, but it cannot be run with it as a factored variable. Okay. And then it's just core.test, x comma y. Okay. And that gives me a correlation of 0.26. Okay. What does that mean? We'll get to that in a second. It gives me my confidence interval, so it's very close to 0. So I don't know how believable this correlation is, right? Because the bottom of the confidence interval is basically nothing, and the top end is large. So we have a range of a correlation from nothing to large. Okay, so not a good, probably not a very believable correlation. It is significant. So how do I interpret? This would be a true dichotomy, point biserial, because you either have entered or you haven't that data. The easiest thing to do is to plot it. So activity, novice. Okay, so make that scatter plot. Oops. It helps if you tell it where to find the data. So what's happening is it's telling me the difference between the two categories. Maybe we should flip it. That'll help, I think. Okay, so I just flipped my plot here. There we go. So what a point biserial does is it tells me the difference between 1 and 2. So it creates a slope or a regression line correlation between being a 1 and a 2. That's all ANOVA does too. So when we've been doing ANOVA, it's telling me the difference between 1 and 2. Right? So I find, like, here's mean 1, it's this score. Here's mean 2, it's this score. R is the difference between the two. So if I calculated the means on this data, I did creativity. I have a mean for group 1 is 0.42, and a mean for group 2 is 0.37. So they're what, 3 points difference? Okay. And the correlation, we figured out, oops, that's tau, sorry, wrong one, was 0.26. Okay, 0.26 is the standardized difference between the two. So all that does is calculate the difference between the two, basically. So point biserial correlation is essentially ANOVA with two groups. So t-test. It's not exactly the difference between the means because, remember, correlation is standardized. All right. But you can calculate them. I find them a little silly because, like, I'd rather know what the means are. That's more useful to me, but you can do it. So when we get into regression with categorical variables, we'll come back to this because that's what regression. If I have male and female, it's just telling me the difference between the two means. Okay. Two last pieces, comparing correlations and partial correlations. So I get this question a lot, like an unreasonable amount of time, even though you can totally Google it and find calculators on the internet that will do this for you. But so maybe you guys won't ask me this question, but I do get it a lot. So how can I tell if two correlation coefficients are different? Because most people learn I can tell this one is significant, this one's significant, but are they different from each other? So you will need to install CoCore, which is a little package that will do the differences for you. And it is like heaven sent, because I was looking at my notes from this last year and it is so much math. So thank you, whoever programmed CoCore. Okay, it is beautiful. And what it'll do is it'll let me compare them. And what, before I get there, what it's doing in the background is called Fisher's, just like the same Fisher's LSD, R to Z. And so if you're ever Googling comparing correlation coefficients, what will happen is Fisher's R to Z will pop up. So, let me check. Correlation coefficient. So two correlation coefficients. Vascular is also a very cool website. Fisher's R to Z transform. So what happens is each correlation coefficient gets translated into Z. The two Z's are subtracted from each other and use that to determine if they're significant, and then it's translated back. It's kind of annoying because it's a lot of math. But if you're ever like stuck and you don't want to pull out Studio, Vascular Stats has it for you. Okay. But what happens to people is this problem. Okay. If the correlations are independent or dependent. Okay. So independent correlations are two separate groups of people. Okay. But they're all usually on the same variable. So if you have gender in there, is the male correlation different than the female correlation different? We're in two separate different groups. I can't be in both correlations. It's independent, just like the way independent T works. Dependent correlations are when people are in both correlations, usually because they're different variables. So is the correlation between exam and anxiety different than the one from exam and revise? I'm in all three of those variables, so it's dependent because I have taken each one of those things. Generally, if you want to think independent involves some sort of categorical variable, you're splitting the data up based on a category. Dependent involves multiple variables of that overlap somehow. With dependent correlations, you can have them be totally overlapping or not. So I could do exam and anxiety and exam and revision. That overlaps by exam. Okay. Or I could do exam and anxiety and revision and some other variable that I don't know off the top of my head that's in that data set. Gender. Okay, those don't overlap at all. Okay. So be sure you know which one you're doing first, because the code's a little different. There are lots of things on the internet that will help you do independent correlations, not so much on the dependent part. Okay. So if you're trying to do one of these and you just want to Google it, make sure you have the right page. Okay. All right. So the sucky part about the independent correlations is the way you have to set it up. So there's no like function in there that's like split by gender. That would be too easy. So what you have to do is first split the data and then join it back together. So we're going to split it up and put it back together again. But we have to put it back together in a list format.
So kind of like minusing it?
In a sense, yeah. Similar.
Please tell me it's easier.
No, it's a couple lines of code. It's not too bad. Right. So I'm going to load the co-correlation library. Okay. And what I've done here under independent correlations is I have subset the data. You guys have done this a bunch of times now, so I'm going to just break it into two data sets based on my categorical data. And hopefully that worked. Oh, no. I first reload the data because I defactor it here. Obviously did these in different parts. Where's the stupid data? There it is. Okay, so rerun line 71 to get our factored data back. And then 83 and 84. Okay. And that happened because I made it numeric here. So I've got my new and my old groups. Remember, it should total up to the liar total. And then what the next line down does, 85, is it creates them in list format. So what I've done is I have the whole data set, and I've broken it into new and old. And what list does is it goes, oh, you have 2 of them. Let's put them together. So it kind of creates you like 2 little mini grocery lists. That's the way I think about it. Okay. So it's got 2 separate data sets stacked together. Okay. So run 85. You'll notice that it's down here under values. And if you click the little down arrow, what you get is one data frame with 3 variables and another data frame with 3 variables. So it kind of says you have 2 different data sets and puts them into one file. It does not combine them back together into one giant data frame. It's like 2 little data frames. Okay. So after you do that, here's the code. Okay. And it has to be written exactly like this, exchanging out x and y and data. So the tilde, so we're going to approximate x and y correlation. This straight up and down arrow that on normal keyboards is above the enter key. And then x and y again. So it's the names of the variables in each data set. So this is list 1 and this is list 2. I'm assuming they're going to mostly keep the same name because you've taken one data frame and broken it into 2. So don't rename the columns is what I'm saying. Data equals my new list. So let's look at that. Not on that slide, but in here. So I have creativity and position. And then the second list is creativity and position. So it's the same correlation compared for our 2 different novice types. So then the data is independent data. Okay, so all I've done is change out x and y for the variables I want. If you want to do this multiple times, you have to do multiple lines. So run that. It gives you so much output. Oh my god. It's kind of out of control. Did yours break?
Yeah, both of ours broke.
Both of them? One second. All right. So in looking at all this output, this is not the crazy one. It's the next one that's crazy. What is going on? It tells you the correlation for the first group is negative 0.21. The correlation for the second group is 0.38. Negative 38, the negative going in. So we got negative 21, negative 38. This here subtracts them. The difference between that correlation is 0.17. And then it gives you a bunch of stuff. It's going to go math. And then here is Fisher's R to Z. So this is the traditional analysis that people do on independent correlations. So the z-score of that difference is only 0.73. So that is a non-significant difference between correlations. So P here is 0.47. The second piece here is a confidence interval of the difference. So it's not a confidence interval for 0.21 or 0.38. It's a confidence interval for this, 0.67. Or I can't. Dyslexia, 0.17. Okay. So the confidence interval ranges from negative score to positive score, and it's huge. So these are not significantly different. So it gives you Fisher's R to Z, so you report the Z value. You report R1 and R2, right, the Z-score, because people can subtract them themselves. And then the confidence interval if you want it. And even the better part, it even tells you if you should accept or reject the null. So if you can't remember the p-value rule, look, not rejected. Now, dependent correlations are easier to run, but oh my god, there's so much output. So it's the same format. You do not have to split the data, leave the data all as one thing. So splitting the data is for independent. So I have different groups, I have to split it up. You would fill in X, Y, and Z. Okay, this is an overlapping correlation example. And they overlap by Y. So this would be my exam to anxiety, exam to revision kind of example. You could also have X, Y, Z, and Q, but they don't overlap at all. So all you're doing is switching out the variable names here and what the name of the data set is. And then I have so much output because it does give you a bunch. So I switched here. I just did one back to the exam data because our other data set doesn't have enough variables. So I'm going to do the difference between revisions and exams and revisions and anxiety. And I couldn't copy all the output because there's a lot. Yeah. You can tell it which output you would like to see most, but I figured it'd be easier to see all of it, and then you would know if somebody asked you for a different one where that output was. But first thing it does is give me revision and exam, so 0.4, revision and anxiety, which is the negative 0.71. So the difference between those two is 1.1. And that's okay because one's positive and one's negative. Okay, so the maximum difference score, I guess, would be 2. Right? Because if one was perfectly negative and the other was perfectly positive. It tells you the other related correlation between the two, which would be exam and anxiety. Another stuff. And then it gives you a bunch of different hypothesis tests for this. Pearson's Z is probably the most popular, but there's a bunch of different ones. Pick your favorite. They mostly all say the same thing, right? They're just variations on different transforms and calculations. I'd probably go with the first one. But if you look at all of them, they have the same conclusion, right? The hypothesis is rejected. And then at the very end, again, it gives you the confidence interval is the same one as independent. Okay? So the confidence interval of the difference is 0.86 to 1.3. So that interval does not include 0. A 0 difference between correlations would be no, the correlations are the same. Okay? So yeah, I know it's a lot of output, but pick your favorite one. I don't know. It wasn't totally clear to me which one was most popular, but I would probably guess Pearson's. And it even gives you the citation. So the name and the year, if you want to cite whoever you're picking the correlation comparison from. So that's nice, at least. All right, questions on comparing correlations. All right. The worst part is the setup for independent ones, because you have to break it apart and put it back together. Last topic. Partial and semi-partial correlations. And this is really actually more important next week, but I figured we'd get into them now. Okay. Partial correlations, so PR, measure the relationship between two variables controlling for the third one. So partial correlation is the answer to the third variable problem. I want to know exam and anxiety controlling for how much they revised their exam. Okay. So it removes the variance due to that third variable. Semi-partial correlation is not so easy. This is SR, is the symbol for it. It measures the relationship between two variables, controlling for the third variable only on one of them. The first one makes more sense. I have an exam, I have anxiety, remove revision from both of those. Second one, not so much. I have exam and I have anxiety, but remove revision only from one of them. Semi-partials are weird. Okay. So let me give you a picture format. So if I'm trying to figure out the relationship between an exam and anxiety, it takes out revision from both. That's partial correlation. If I'm trying to figure out exam and anxiety, but I only want to remove revision from exam, because they're revising their exam, they're not revising their anxiety. So that would just take out the variance due to revision here. That would be a semi-partial correlation. Why would you do these? Well, partial correlations are really popular for the third variable problem. So it removes the variance in both variables due to some third or fourth or fifth or sixth other variables. And that is actually how regression coefficients get tested. So next week when we're talking about regression, we're going to come back to this idea. Semi-partial correlations, I don't really know. It's a thing. People do them. I guess if the relationship here were 0, a semi-partial correlation would make more sense. So there's actually no relationship between revision and anxiety, so it's only controlling an exam. I don't know. Most people prefer parts. Also, mathematically, partial correlations are always larger than semi-partial correlations, and we always want to look like things are more significant, right? They're bigger and better. So people pick partials also because they're bigger. And next week when we talk about these, we'll talk about how they're actually mathed. and draw lots of Venn diagrams. But for right now, we're just going to talk about how they theoretically work. And if that doesn't make sense, here's another picture. Okay. So I've got exam performance and anxiety. This would be straight regular correlation. Exam performance and revision, still correlation. This would be example of partial correlation only. So I am looking for exam performance and anxiety, ignoring the overlap here with revision. So this little white square here gets ignored. It doesn't count. Okay, so I'm looking at exam and anxiety, ignoring the white square. But the other cool thing about partial correlations is it also ignores the relationship between exam and revision. It's the purple square here. And so basically it's a error variance reduction. So partial correlations help you out. They're larger because you're taking out some of the variance that you already know what happened with it. Does that kind of make sense? Like this is due to revision, so ignore it. So the amount of leftover error is smaller. So people like them for that purpose. All right. So the way to do those is in the PP core package. You know, part and partials is what I think it stands for. In the output for SPSS, it's listed as part and partials, which is not confusing at all, right? Because why aren't they called semi and part? I don't know.
Because of alliteration.
Yeah, I don't. It's confusing. I can't even remember. I always have to think which one's bigger. Okay, that's partial. And then, fortunately, the code for it is the same as core. It's just got a P in the front. So it's going to be Pearson. And then the core function actually gives you all three things at once. Estimates, which is R, or PR, p-values, and statistics. Okay. So let's try that. Okay, so I got P core. Yeah, thanks. Okay. So I'm going back to my exam anxiety data set, and I'm dropping those columns. So let's do partials first. So it gives me everything at once, which is beautiful. Now, these are easier to interpret than the next ones. So in a partial correlation, the relationship between revisions and exams is 0.13. That controls completely for anxiety. So revisions and exams are not significantly related after you control for anxiety. So it doesn't matter how much they're revising it, it's not affecting their overall exam score. The relationship between revisions and anxiety, though, is a fairly large correlation. So as I revise more, my anxiety goes down. That controls for their end exam score. So that's controlling for how well they did on the exam. And then the last one, exam and anxiety is significant, but it's a smaller correlation than we saw before. So that controls for how much they revised it. So these are the relationships between the variables controlling for the other ones.
What did you say that value was? Is it the p-value or the
P-value
power?
here?
For,
P.
For estimate.
Estimate is PR. So the partial correlation. P-value is P. Statistic, I think, is probably T. Yeah. Okay, so semi-partials is SP. So same format. But the interpretation is a little bit more difficult. So I run SP, shows me the exact same output. So you just have to remember if you're running partials or semi-partials. So the way semi-partial correlation works is it's the correlation between 1 and 2, given that 2 and 3 are correlated. Nothing with 1 and 3. So the first column, so this number, is 1, and then 2 and 3. So it's the correlation between revisions and exams, given that exam and anxiety are related. So remember we said the top half of the triangle is the same as the bottom half of the triangle, because correlations, it doesn't matter if I do revise first or exam first, and then until the end. So you'll notice that the correlation between revisions and exams, given anxiety, is not the same correlation as exams and revisions, given anxiety. Right, so I got 0.12, 0.09. So what's happening is you have to interpret going across. So this is revisions and exams, given that anxiety and exam are correlated. And then revision and anxiety, given that anxiety and exam are correlated. Okay. So it is never given that the first one is correlated with these two. Okay. So this one would be exam and revisions, given that anxiety and revisions are correlated, and exam and anxiety, given that anxiety and revisions are correlated. Okay. Does that kind of make sense? That's the hardest part about this, is figuring out which one is it controlling for. So the first one correlated with the second one, and the second and the third are being controlled for. And then the first one correlated with this one, but these two are still controlling each other. Okay. So the columns are being controlled for, and the rows is always number one. I actually whipped out SPSS to test that theory, because there's not a whole lot of documentation on this package. And so that's the difficult part to interpret them. Okay. But I can still see which ones are significant. So even controlling for their exam score, revisions and anxiety are still significant. And so you'll notice that the partial correlations are bigger. So 0.65 versus 0.560. Not a whole lot bigger, but they're going to be bigger than semi-partial. And we'll get into why that's true mathematically next week. Okay. So, sum up. We covered Pearson's, spindles, Spearman, Kendall, point biserial correlations, partials, semi-partials, and comparing correlation coefficients. Okay, so lots of different things about correlations.